I believe we are actually broadcasting right now, so I'll wait a few minutes for more attendees to join and then do an introduction.
Yeah, sure.
Okay.
And where is the chat on? I can see the chat chat box. Is this? No.
It should be a drop-down menu towards the lower portion of this GoToWebinar interface.
Okay, I see. I think you cannot see my screen at the moment, isn't it?
That's correct. Right now, I don't see a screen.
Okay. How should I start presenting? Can I ask you to request me to present my screen? Oh, that too. Thank you.
Yep, I see your screen now.
Perfect.
Great. Okay, I'll just wait 2 minutes and then do the formal introduction. I think more attendees are starting to join now.
Sure. Should I start just on time?
Sure. I think it's just about time now. I'll go ahead and introduce you, and more attendees should be filtering in. But thank you. Hello, everyone. Thank you for joining us today for Rethinking Object Detection with Alisher Abdukov, Teaching Fellow and Board Director at Tokyo Data Science and Machine Learning Tokyo. We will begin in just a minute or two. As a quick reminder, a brief survey will follow at the end of the session. We invite you to share your best moments at the virtual conference on social media, Facebook, Twitter, etc. Please use the hashtag ODSCAPAC. The post with the highest number of likes and shares will win an all-access pass to ODSC East Virtual. All of your feedback help us shape future conferences. Thank you, and please join me in welcoming Alisher Abdukov. We will now begin the session.
Hey, thank you very much for the introduction, and welcome everyone to my tutorial session. We will be discussing about rethinking object detection in this tutorial. So the topic is rethinking object detection, and today we will be discussing about the history of object detection as well as the future directions regarding the research of object detection. My name is Alisher Abdulhayev. I'm a board director at Machine Learning Tokyo. and also working as a full-time engineer, computer vision engineer at Browsin, which is the AI-powered social fashion app. And at the same time, I'm pursuing my PhD at the University of Tsukuba in computer vision lab. I'm a supervisor as Professor Fukui, and I'm also like teaching fellow at Tokyo Data Science, which is the online data science school. And if you wish, you can follow me on Twitter, Alishar AI. I would like to talk about Machine Learning Tokyo, what is it, and what we do in Machine Learning Tokyo. Machine Learning Tokyo is the award-winning nonprofit organization based in Japan, and MLT is dedicated to democratizing machine learning, which we do various initiatives such as open source. We initiate open source projects. We organize study sessions and meetups, and we support almost 8,000 members from all over the world. And if you would like to join Machine Learning Tokyo, you can visit the following links. You can visit our webpage, our blog, and other links on MLT Starter Kit. And I would like to talk about only 4 of the projects what we are doing at MLT. The first one in which we annotate the research paper with extra explanations, illustrations, and doing some and deploying machine learning models into edge devices. And also, like this year, Edge AI team won a prize from one of the competitions. And as for research, last year we have published 2 papers at New York 2019, and we are going to publish more papers in the next year. And after introducing me and Machine Learning Tokyo, I would like to give a brief outline of this talk. In the beginning, we will be discussing about brief object detection history, and then I will be talking about evaluation metrics and data sets, and this would help us to understand how to assess the performance of object detection models, and then I'll be talking about neural networks as well as convolutional neural networks, and then I'll give a couple of examples for deep learning based object detection algorithms, and then I'm going to show the object detection training, one example for object detectors, and we will see an implementation of object detection. And then at the end, we are going to talk about the future of object detection, in which what we should do to make the object detection more reliable and more interpretable in the future. And then we will have 15 minutes for Q&A. Okay, then let me start with the history of object detection. Actually, object detection is very important and very important topic in computer vision. Because object detection is about localizing objects as well as declassifying that localized region. And this is important because once we localize the object in an image, we can do lots of computer vision applications. For example, if we detect faces on an image, we can do face recognition, we can do face matching, we can do face tracking, or if we detect the persons in an image, in a video, we can track the person where he or she goes, and track the locations of the particular person. Or like if you localize the objects in a street, we can use this. We can do autonomous driving applications. so that we can track the people, we can track the objects, and so on. So the object detection is a computer vision technique in which we localize the object, and after localizing the object, we classify that object into multiple classes. As I said, object detection has various applications in several domains. For example, it's also very applicable to robotics, autonomous driving, surveillance, face recognition, and so on. So actually, object detection has a long history. It even exists before the deep learning, which we call the traditional approaches, pre-deep learning or traditional approaches. And for example, in 2001, there was the paper about face detection by Viola and Jones. And Viola and Jones detector proposed to detect the faces very, very fast. Of course, the history of object detections has longer history from maybe 30 or 40 years. But in 2001, Weil and Jones proposed a face detection algorithm, which was very fast and accurate enough. In 2006, there was another approach, which was following the Weil-Jones detectors approach, and done some contributions like histogram of oriented gradients for feature extraction. And in 2008, there was another face detection approach, which is called deformable part-based models. And of course, we are going to talk about each of them separately. And let me say that in three of these approaches, the localization done by sliding window approach, in which we have a template bounding box and we slide that bounding box over the image. That's why we call it sliding window approach. And as for classification, the features were handcrafted and feed into the classifier to classify if this is a face or not. Okay, and the Weil-Jones detector, again, the localization was done by sliding windows approach. And as for classification, handcrafted features extracted and feed into the classifier. The contribution of Weil-Jones detector was integral image. I'm not going to deep into integral image in this tutorial, but that approach actually makes the face detection very fast. And feature selection and detection cascades. And next one was histogram of oriented gradients detector. And again, the localization classification approaches were almost the same with the Weil and Jones, but there was a few contributions on this paper, which makes the feature extraction scale invariant. That means even though image is big or small, we can still detect the faces, which means scale invariance. Yeah, in this case, the input image into multiple scales. And another one was the deformable part-based model. This is again the same in terms of localization and classification with the previous ones. And the contributions of this approach was actually it's kind of extension of histogram of oriented gradient detector, and it follows the divide and conquer approach, in which it divides the objects into different parts and try to learn that parts instead of detecting the whole object. For example, for face detection, it learns the eyes, nose, and mouth, or hair, or ears. So technically, it learns properly decomposing the objects into their parts. You can think of a car as like a combination of parts like window, door, wheels, and etc. After giving a very, very brief history overview of object detection, I would like to talk about evaluation metrics and as well as some benchmark data sets. if you already work on object detection, you should know all these topics, like how to evaluate the object detection and what benchmark data set do we have to evaluate our model. But if you are new to object detection and topic, then it would definitely be informative for you. Okay, let's start with evaluation metrics. Actually, evaluation metrics are very important to test our machine learning model performance. And saying that there's no single magic performance metric for all machine learning tasks. So that means, like, if you have different problems, if you have different tasks in machine learning, you have to have different evaluation metrics. And I would suggest, like, to deciding on evaluation metric in the beginning of your project. It could be either research or it could be either any production project. In either case, I would suggest you to decide on evaluation metric first and then start doing the project, because otherwise, if you don't have a proper performance assessment, then you wouldn't be able to know the how to proceed. So that's why evaluation metric is, for me, the most important part of machine learning, I guess. And then, yeah, there are lots of evaluation metrics, but I will go through over some of them, and especially the ones which are important for object detection. I'll be talking about true positive, false positive, true negative, false negative, and accuracy. As you already may know, the accuracy is very important for classification. But for object detection, we need to know about precision and recall. And then I'll talk about intersection over union, average precision, and mean average precision. Okay, so as I said, there are a couple of evaluation metrics for different but I think this 4 of them, which are true positive, true negative, false negative, and false positive, are kind of building blocks of most of the evaluation metrics. So that's why it might be a good idea to understand what they are, so that we can understand accuracy, so that we can understand precision and recall. And for object detection, particularly for object detection, all we need to know about is these 4 building blocks of evaluation metrics. Okay, so here's this sample scenario. Let's say you have a ground truth vector, which means the correct vector of classification IDs. For example, if you have 1, 0, 1, 1, 0, 1, 0, 1, 0, and if your model predicts all 0, then what would be the true positive, what would be the true negative, false positive, and false negatives? So true positive means your the number of predictions which Can you hear me? Can you confirm if you can hear me?
Yes, we can hear you again now. It went froze for about a minute there.
Oh, sorry. My apologies. Can I share my screen again?
Yes. I think we can see your screen.
Oh, okay, got it. Got it. Okay, then let me recap. Okay, let me define what true positive, true negative, false negative, and false positive metrics are. True positive is when your model predicts the sample as a positive, and if it is actually correct, then it's called true positive. And false positive is when your model predicts a sample as a positive, and if it is not a positive, then that's the definition of false positive. And true negative is when your model predicts the sample as a negative sample, and if it is actually correct, then it's called true negative. And false negative is when your model predicts the sample as a negative sample, and if it actually was not correct, then it's called false negative. And in the scenario on the left, our model predicted all zeros. In this case, true positive is 0 because our model didn't predict any of the samples as a positive. And similarly, in false positive, it's again 0 for the same reason. And true negative, our model predicted all negatives, and only 3 of them was this one, and this one, and this one. And this one, and this one was actually negative. So that's why true negative was 0 because of this sample. And false negative, we predicted negatives like this one. Oh, I'm sorry. False negative is 4 because we have this one, which our model predicted the false, but it was not correct. This one, and this one. That's why this is 4. And for true negative, this is we predicted as a negative, and it was correct. This one, and this one. And this is the scenario 1. And in the scenario 2, we have the same grand truth label, and our model predicted all ones. And in this case, true positive is 4 because of this one, and this one. And the false positive is 3 because we predicted as a positive and which were not correct, which is this one, and this one, and this one. And as for true negative and false negative, all 0. And in terms of accuracy, as you see, the accuracy on the left is 43, and accuracy on the right is 57, and which means like in these two scenarios, the thing is our model didn't learn anything at all, because like in this scenario 1, the model predicts all zeros, and in scenario 2 it predicts all ones. That means our model didn't learn anything at all, but the accuracy value is different in these two scenarios, and which means okay, let's see another two scenarios as well. Again, we have the same grand truth labels, and in this case, the predictions are not all zeros or all ones, but instead the model starts to learn something. So in this case, the accuracy is 28, and in the scenario 4, the accuracy is 86. So what I mean by showing these scenarios is accuracy is as a good performance metric for classification, but sometimes we need more sophisticated evaluation metrics because like in the previous scenario we have almost the same thing in the first one, and the model didn't learn anything and predicts all zeros, and in the second one again it didn't learn anything and predicts all ones, but the accuracy value change differs from between these two scenarios. So that's why we conclude that we need to have another evaluation metric for better better evaluation. And let me ask you a question. So on the left, you see a picture in which the doctor says you are not pregnant to a woman who is actually pregnant. And this is the false alarm, false negative error, because like she's actually pregnant, but doctor says she's not. And in the right side, you see another kind of error, which is false positive. And that means doctor says to a man that he is pregnant. And this is actually a false positive error. And so let me ask you, which is the worst? Which is worse? So the one on the left or the one on the right? So actually, it's difficult to answer this question because like both cases are very like bad scenarios, because on the left, if doctor says she's not pregnant, then there could be some problematic cases, but on the right there would be kind of another problematic cases. So we have to differentiate these two types of errors, and for that reason we have another evaluation metric which is called recall and precision. Recall and precision is a bit more sophisticated evaluation metric to differentiate the performance of two different models. So the recall is answers this question: what proportion of actual positives was predicted as correctly? Or in precision, precision answered the question: what proportion of positive predictions were actually correct? And here you can see the formula of recall and precision, and it might be a bit difficult to get the idea in the beginning, but let me show you another example for you. And okay, here we have exactly the same scenario, two scenarios with the previous slides, and on the left is exactly the same scenario, and in this case the recall and precision is 0, which means it can show that our model doesn't do anything at all. And on the right, recall and precision, recall is 1, precision is 0.57. Recall is 1 because we could catch all the positive samples, this one, because our model predicted all samples as a positive. That's why the recall is 1, and precision is almost 1.5 because the predictions precision is almost 1/2, because like we have 1, 2, 3, 4 true catches, and we have 1, 2, 3 negative catches. So that it's the ratio of 3/4, not 3/7. And this is another scenario which is exactly the same with the previous one. In this case, the recall is 0.25, precision is 0.32, and in the last scenario, recall is 0.75 and precision is 1. Precision is 1 because like all our predicted positives were actually correct, so that's why we have 1. And we have recall 0.75 because we could catch only 3 of the actual positive examples. Like there were 4 positive examples and we could catch only 3 of them. That's why the recall is 0.75. As you see, the recall and precision is more information about the model performance rather than the accuracy. And once we get the idea of recall and precision, let me say that recall and precision is the 2 building blocks of object detection evaluation metrics. If you understand what does precision and what does recall do, then the rest of the evaluation metrics would be much easier to understand. And one of them in object detection is intersection over union, is a metric to define the localization performance, and it gives some idea about how well the bounding boxes fit to each other. In the figure on the top, you see the intersection over union visualization, if you have two bounding boxes, and on the numerator you will have the intersection area, and on the denominator you would have a union of two bounding box areas, and this matrix is called intersection over union. And on the bottom you can see a figure in which there are three intersection over union values. On the left you see 0.4, which is not well fitted to the green bounding box, and in the middle you see almost good intersection over union value, which is good enough to accept as a correct detection. And on the right there's excellent intersection over union value, in which the two bounding boxes are almost fit to each other very well. And in intersection over union we have to define a threshold in which we accept the bounding box as a correct catch or not. For example, if we define the threshold as 0.7, then this one and this one would be accepted as a correct localization, but this wouldn't be accepted as a correct because 0.4 is less than 0.7. And intersection over union is also used in non-maximum suppression, and to discard the multiple bounding box at the same area from the same class. That means there could be different lots of bounding boxes in the same area, and non-maximum suppression suppresses some of them according to the intersection over union as well as the detection probability. And yeah, let's have a visual example for recall and precision in the face detection topic. Okay, recall is answer the question about the face detection is how many of these faces did we detect? So if you have a face detection model, and the recall would define how many of these faces did we detect. Yeah, and as for precision, we answer the question of how many of the detected faces were actually correct faces. For example, in this scenario, you see we could detect all the faces, and there's no false detections, and that means the recall is 1 and precision is 1, because we did very well. We could detect all faces, which is recall is 1, and none of the detections were not negative false. Then that's why the precision is 1. And in this scenario, on the right top, you see we could detect only 3 of the faces. That means the recall is 0.6, and precision is again 1, because even though we missed some of the faces, but we didn't detect any of them as a false, right? So any of our detection was not false. That's why precision is still 1. And in this case, actually this is the same. Sorry. Yeah, it's same, but the different thing is in this one we could detect this person, but in this one we could detect this person. So recall and precision doesn't differentiate between which people faces has detected or not. So the recall and precision values are exactly the same between these two scenarios. And in the last one, you can see that we still could detect 3 of the faces, but there's also another false detection. That's why precision is not 1 anymore. It's 0.75, because we detect 1 false detection, but the overall detected faces were 4. That means 3 over 4, 0.75. And recall is same with these last 3 examples. I hope this gives more intuition about recall and precision. And let me proceed with the average precision. In object detection, as I said, the precision recall is very important. And another metric is average precision, in which we have prediction probabilities, prediction scores, and we threshold that scores according to some confidence thresholds, and we compute the different precision values for different confidence thresholds, and then we take the average, and that is called average precision. And there's another metric in object detection evaluation, which is mean average precision, which is the average precisions over all classes. Since in the face detection, since we only have one class, which is a face, in that case, average precision would be equivalent to mean average precision. And let me briefly go through how to calculate the average precision. Okay, so your model, let's assume your model detected this bounding boxes with this confidence thresholds. And what you should do is just rank the thresholds from 0.94, 0.72, 0.61, and so on, and answer the question if it was correct or not. Okay, this one was correct, this one was correct, and 0.3 was correct detections, but other two was not correct. And calculate the precision. Okay, when you set your confidence threshold to, for example, 1, your precision would be 1. And when you set it to 0.94, your precision would be 1, because you detected only one face, and the precision would be 1, but the recall would be 0.2, and so on. If your confidence threshold is 0.72, then your precision would be still 1, but your recall would increase from 0.2 to 0.4, and so on. You should calculate all these precision and recalls, and then according to the thresholds, you can change your threshold from 0.1 to 0.9. It could be finer. There could be finer steps between, for example, 0.01, 0.02, etc. But just for visualization, let's have only 9 different thresholds. And for each threshold, you should calculate the precisions like this, and take just the average of these precisions, and that would be your average precision metric for your object detection performance metric. And as I said, since there is only one class, that's why average precision would be equivalent to mean average precision. And as for benchmark data sets, we have Pascal DOC, which is quite old data set, and in which there are 20 different classes, and there are like more than 8,000 images with almost more than 20,000 objects. And another more complicated data set is COCO data set, in which there are 80 classes and more than 200,000 images with 1.5 million objects. And there is one of the recent data set is Open Images data set, in which there are 600 classes with almost 2 million images with 60 million objects. It's too big data set, but most of the research papers compare their results according to COCO data set. Okay, after seeing these evaluation metrics, let's go with the neural network and convolutional neural network, which is very important for state-of-the-art object detection. Important to understand the recent state-of-the-art object detection models. Okay, let me very briefly go through the artificial neural networks. Artificial neural networks are computing systems inspired by biological neural networks, in which we have edges, we have connections between edges, and we have an input data, and we process the data to get a prediction result. Neural networks can be used as a classifier. For example, if you feed this handwritten digits, your neural network can predict you whether it's 0, 1, or any other number. Actually, neural network does this couple of transformations, and it transforms the input data into different representational space, which occurs at every layer. And then at the end, you can do a classification or regression to classify or make a regression on your data. And there's another family of neural networks, which is called convolutional neural network. Convolutional neural network differs from the conventional neural network because instead of having this connections between layers and between nodes, we have another kind of computation going on each layer, which is called convolution operation. And at the end, we will have again the kind of conventional neural network, which we call it fully connected layer. So convolutional neural network consists of convolutional layers and then fully connected layers at the end. And so the first part is used for feature extraction. We have a visual data, we extract some visual features, and then at the end, we classify those extracted features into different classes. So we can say the convolutional layers are for feature extraction and fully connected layers are for classification. And here's the one example of a convolution operation. I have chosen the edge detection kernel, which is there's the kernel. There's 3 by 3 matrix, which we convolve over image. Convolving means having a window and slide the window over all the image, and then extract some of the features. For example, in this case, we have edge detection, or you can say edge extractor, which extracts some edges on this image. So you see, here's my picture, and you can see there's some edges extracted from my picture. And here's another one, is like if you have 2 classes to be classified, cat and dog, you feed in the images from different classes, and your neural network would map that image into different representational space, and then at the end predicts whether it is cat image or dog image. Yes, CNNs are very great tool to extract visual features, which is going to be used for classification or object localization or regression or something else. Convolutional neural network can be trained in a supervised manner. By supervised, I mean you will give a pair of images and corresponding labels. But the thing is, in order to train this convolutional neural network, you would probably need a lot of images. For example, if you have 2 classes, maybe you should have more than 1,000 images to classify those images correctly. And then another term, which is called deep convolutional neural network, which is exactly the same with deep neural networks. Yeah, deep convolutional neural network is a deep neural network with convolutional layers, you could say. In deep convolutional neural network, or DCNN, we have lots of multiple layers, and that's why we call it deep. And it takes an image and assigns some weights to the pixel values, and map the input image into different representation space, and do the same thing at every layer. For example, there's a deep convolutional neural network called VGG19, in which we have 19 layers, which means we do the same thing 19 times at every layer. And there's another very advanced network, which is called ResNet 152, in which we have 152 layers. And here's some of the other deep convolution neural network examples for AlexNet, VGG16 or 19, Inception, SqueezeNet, MobileNet, Exception, DenseNet, and ResNet, and different versions of ResNet like 18, 50, 101, and 152. Okay, so the deep convolution neural networks were good at visual feature extraction, and so that means it is very useful for object detection as well. Just to remind, the conventional object detectors were using this sliding window in which they predefine a bounding box and slide that bounding box over an image, and then once it decides that the image is correct, the region is corresponds to a particular class, then it detects that object. But in deep learning based object detection algorithms, there are different approaches to detect the objects. Okay, here's the timeline of deep learning based object detectors. In 2014, there was very huge jump in performance of object detections, which with the RCNN paper. And in 2001, 1 year later, there was proposed different versions of RCNN, which is fast and faster RCNN, in which they make the RCNN much faster than the original one. And in the next year, in 2016, there were two object detections called YOLO and SSDE. And 2018, there was RetinaNet proposed. And last year, there was another object detection approach is proposed, which is called efficient depth. Of course, these are not the only object detectors in recent years. There are more than maybe 100 different object detectors, but these are kind of very important milestones in object detection research. Okay, before jumping into explaining different algorithms, I would like to talk about one-stage and two-stage object detectors, in which, we have to know the difference between one-stage and two-stage object detectors. In two-stage object detection algorithms, and there are two networks, there are two steps. The first one is region proposal, which corresponds to sliding window in the conventional object detections. And the second stage is classification. Once we propose a region, and the second one would classify if this region corresponds to a particular class or not. Two-stage object detectors are much slower than the one-stage object detectors, but the performance are mostly higher than the one-stage object detectors. And in one-stage object detector, instead of having two different steps, we have a single network, a single pipeline to sample the possible regions and classify those regions at the same time. So that's why it works faster and it's much simpler, but the performance could be a bit lower than the two-stage object detectors. RCNN, the first deep learning-based object detector, was two-stage object detector. RCNN stands for region-based CNN, in which the one network proposes regions and another one extracts features for each region. For example, if you have this image, and the first step proposes a couple of regions, something like that. And the approach for region proposal is selective search. And for every proposed region, the next step gets crop those region. For example, here, crop this man body region, and then feed into the convolution neural network, and then tries to classify into different classes. And And in the next year of this RCNN, there was fast RCNN, in which they extract features of the entire image instead of extracting features for each region. They extract the features of entire image, as you see like this, and then region proposal, again done by selective search on CNN feature maps. So we map the input image into different spaces, and then do the region proposal on that space instead of pixel space. So, and this contribution make it much faster compared to the original RCNN. But again, in the same year of fast RCNN, there was another proposal, another approach, which is faster RCNN, in which the region proposal was also trainable, which boosts the performance and integrate the region proposal network into CNN model, in which, like, that means the speed was faster because the region proposal was not done by selective search anymore, but instead the region proposal was done by neural network itself. And there was another version of RCNN detection, which is called mask RCNN. This is a bit different from object detection, but we can call it image segmentation or instance segmentation, in which instead of like predicting bounding boxes, the model predicts the defined boundaries of the image, of the objects, which is called object segmentation or instance segmentation. Okay, this are our two-stage object detectors, which should be slower than the one-stage object detectors, but the performance should be high enough. And there in the 2016, there were proposed two different object detections. One is YOLO, you only look once, and the SST, single shot multi-box detector. In YOLO, for example, there's no region proposal network, but instead they predefine this dense grids, predefined grids, and then use those grids as a region proposal by using the convolutional neural network features. So that's why there's no region proposal, and it works much faster than the RCNN one. And in SST, SST uses pyramid of features in CNN, and it can detect the objects in various sizes. For example, in YOLO, you see there's no like varying sizes of these grids, but in SST, you see that there are different aspect ratios and different sizes could be detected in the SST one. And there was another object detection, which is my favorite object detection, which is called RetinaNet. They again use the feature pyramid to be able to detect the objects in different scales, and as well as they proposed a new loss function, which is called focal loss, which gives higher weights on hard examples and gives lower weights on easy examples, which means if the examples are easy enough, then network shouldn't learn much about that cases. But if the objects are hard to detect, then it gives higher weight so that network can learn more, can work on more harder examples. So the RetinaNet is, I think, one of the greatest object detections so far. And I haven't talked about detection efficient DET. In efficient DET, the difference is they construct the network architecture by neural architecture search, which is the computation, the overall computation would be less, and it can be run on edge devices. So that's why they call it efficient detection. And And yeah, I would like to show some implementations of face detection. And before going through the implementations, I would like to talk about the MTCNN face detector. And as for face detection, I think MTCNN is one of the greatest face detection algorithm. And again, this is my favorite face detection algorithm. MTCNN is face detection algorithm, which detects the face boundaries as well as the landmarks, 5 landmarks. The MTCNN leverages the inherent correlation between face detection and landmark detections. It is very, very fast because it uses very shallow cascade CNN architectures. So there are three networks in MTCNN, which we call it PNet, RNet, and ORNet. And in the end, ORNet gives a result of face boundaries as well as the landmark locations. Landmark localization is important for face alignment, and face alignment is important for face tracking, we could say. And as I said, there are 3 different networks in MTCNN, which each of the networks are very, very shallow networks, like 4 or 5 layers at each network. And before feeding the image into the PNet, and the MTCNN construct multiple scales of input image and construct the image pyramid with different resolutions and feed those different scale versions of input image into PNet. And PNet is called proposal network, which proposes candidate face regions in the image, and gives the output of the PNet into RNet, which is called refine network, in which RNet refines some proposed bounding boxes, and then it gives the output. For example, the input image was this, and PNet proposed this one, and there was a non-maximum suppression, which means non-maximum suppression suppresses some of the overlapping bounding boxes and gives an output of this, and this output is fed into the RNet, and RNet again discards some of the bounding boxes, or you could say refine some of the bounding boxes, and then again do the non-maximum suppression, in which we will have this output, and this output would give into the ORNet output network, and output face bounding boxes. ORNet gives the output face final output face bounding box as well as 5 landmarks. And in MTCNN, they use two different data sets. One is wider face. Wider is very large data set for face detection, and there is another data set for face landmark detection. And I'd like to show some codes on face detection. It should be okay, quick enough. Okay, so luckily we have MTCNN on PIP, and we can install the MTCNN by just typing PIP install MTCNN. And in this line, we're installing the MTCNN package, and then let's import some of the libraries like OpenCV and MTCNN, as well as the image showing image on Google Colab. And okay, after importing these libraries, let's download 2 images. So one would be this one. I can show you here. One image would be this one, and another would be much complicated, much difficult example, which is the selfie example, in which you can see lots of people. And yeah, let's download these images and rename the files as test image 1 and test image 2. let me download the images. Okay, we have done. And here I would like to define a function which shows the image. Like we have downloaded the image and we would like to see the images. And this function takes two arguments. One is image file name as well as downscale value. Downscale value is like if it is 1, then the function would show the original image. If it is 2, it will downscale by 2 and then show the smaller image. For example, let me show you this one. So I call the function with downscale 1 and downscale 2. That means the first image would be the original image. The second image would be half size, in half resolution. Or we can do the same for image 2, which was the large selfie image. Yeah, you can see the original image and the rescaled image. And here I would like to define another function, which is detect faces. It takes an argument of image data and detects the images by anti-CNN face detector. And yeah, let me define this function and let me call this one. So image downscale 1 was the image of this image, original one with original resolution, and you can see these faces are detected in anti-CNN face detector. Yeah, you can see they're very, very tiny faces here, and here, and anti-CNN can still detect very, very small faces. And this is very impressive that this face has been also detected, even though it's not frontal view, and it can still detect faces. So yeah, anti-CNN does very well on face detection. And here's another function which draws the landmarks on detected faces. Let me define this function and let me show you. Yeah. Okay, you see in this one we had only face bounding boxes, but using this function we also plotted the landmarks on face regions. This is how it works, how anti-CNN works. And let me go back into the slides because we have a bit more slides to discuss. So yeah, so far I went through the history of object detection and the state-of-the-art object detections. And now I would like to talk about what should be the future of object detection, which is the topic of this session. Even though the topic was rethinking object detection, it was very important to know the history, to know the different evaluation metrics, and to see the different perspectives. And I have listed four important points of future directions for object detection algorithms. The first one is uncertainty. The second one is better evaluation metrics. Should we come up with the different evaluation metrics rather than the mean average precision? And then another problem is continual learning, which means learn to detect new classes on top of previously learned ones. And another one is adversarial attack problem. I think the object detection, or maybe in general, deep learning should address this adversarial attack problem. And regarding the uncertainty, I think I will go through about probabilistic object detection. Okay, let's talk about uncertainty a little bit. Probabilistic object detection is about detecting the objects and quantifying the spatial as well as the semantic uncertainties of the detections. For example, in the previous object detections, we had bounding boxes, right? There was very certain results, bounding boxes and class assigned to that bounding box. But in the probabilistic object detection, the idea is to detect objects by quantifying the spatial uncertainty, and that means there shouldn't be like very certain bounding box, but there should be some kind of uncertainty in spatial and as well as in semantic manner. So semantic manner means the label uncertainties. For example, in this image, you can see the spatial uncertainty here, in which instead of having bounding box, there are two corners of the objects, and there's some kind of uncertainties defined by Gaussian distribution, two-dimensional Gaussian distribution. And on the right, you can see the label uncertainty, which means we had this object, right? We have this bounding box with some kind of spatial uncertainty, and in this region, there's also label uncertainty, which means the distribution of different class probabilities. And the paper was published last year, and this year there was a competition about the probabilistic object detection in ECCV 2020. And the idea is, yeah, as I said, let me repeat, the idea is to have detection doesn't have to provide information about where and what an object is, but there should be another additional information, which we can call it spatial and semantic uncertainty. If we wouldn't have this kind of uncertainties, then we can fail, and our detections could be overconfident or underconfident. Overconfident means if one algorithm is overconfident, that means it may predict the correct predictions, as well as sometimes it can predict some samples very confidently, but that predictions may not be correct. So the overconfidence is very important problem in deep learning in general. Yeah, as I said, this is the semantic uncertainty, categorical distributions over labels, and spatial uncertainty. And I'd like to show you a video of this from the challenge of probabilistic object detection. Yeah, so in general, in deep learning, uncertainty is important because we have to avoid overconfidency almost in all algorithms. Because if you have overconfidency, then the decision boundaries of classes would be there would be very sharp transition between decision boundaries. That means your system tend to predict the classes incorrectly. And the next one, which the object detection should address, is different evaluation metrics. And in the same paper as the previous one, which was probabilistic object detection, they also proposed a different evaluation metric, which we call it probability-based detection quality measure. And this metric is mainly for probabilistic object detection evaluation, but it can also be used for non-probabilistic detectors. For example, it can also evaluate the YOLO, SST, RetinaNet, or MDCNN detectors. PDQ is explicitly evaluates the reported probability of the true class via its label quality component, and it jointly evaluates the spatial and label uncertainty quality at the same time, as well as the foreground and background separation quality. Because there was uncertainty in spatial domain, then we could make a separation between foreground and background, and we can evaluate, the PDQ can evaluate this as well. And PDQ can also evaluate the number of true positives, false positive, false negative detections. So one of the most important point is PDQ doesn't rely on fixed thresholds. Just remember, in previous average precision calculations, we were considering different thresholds, right? We had fixed the threshold and get the precision values for each threshold, and then take an average, and we call it average precision. But PDQ doesn't rely on any fixed thresholds, and by doing this, it can provide optimal estimate of detections of the objects. And the next thing which the future of object detection should focus is continual learning. Actually, this is not special for object detection. So it's again the general problem of deep learning, in which, like, when we have, let's say, when we have a classification model, and when we train that model on, for example, 2 classes, and when we have the third class after training the model, we have to retrain the model from scratch. So this is the problem of continual learning. In continual learning, as a humans, we learn one object, and then we learn another object, and we can easily learn the third object, right? Without the need to learn this previously learned classes. So continual learning is about learning to detect different objects on top of the previously learned objects. The current object detectors are still domain specific, in which when you train your model on a specific data set, on a specific classes, you can use that models only on that class of objects. But in continual object detection, we should be able to learn different objects on top of the previous one. Here's the very nice illustration about the continual learning. For example, task 1 is about cars, and you train your model, and you can test your model on this image, and your model can detect the car because you had only car images. And in that task 2, you have some another domain which is about dogs. And when you give this one, when you give this data set to your pre-trained model, your model should be able to detect car from the previous task, as well as the dog from the task 2, and so on. When you have horse or some different images, then your model should be able to detect horses, persons, etc. And another problem is adversarial attacks, and it's a rather general problem, not specific to object detection algorithms, in which you see, like, on the top left image, and there's a face, there's a person, and there was a very small patch on top of his nose, and the face detection algorithms failed to detect this face because of some weird modification on the face representation. So this is called adversarial attack. So yeah, and probably model fails to detect faces, because in training data there's no such weird examples in training data, and the model didn't learn this kind of things as the faces, so that's why it fails to detect the faces. And on the bottom right, you can see a person detector, and on the left of person, the model can detect this guy as a person, but it cannot detect the guy on the right as a person, because there was a very like adversarial or like weird patch on his body. So this is actually, for humans, there's no problem at all to detect this as a person and this as a face. But for object detections, current object detections, or in general in current deep learning algorithms, and this is a very problematic case. And there's a very like real world example about adversarial attack, in which you see on the left there's a stop sign, and in the right there's another stop sign, but with a bit modifications. And Tesla cars autonomous driving algorithm fails to detect this as a stop sign, but instead it detects a speed limit sign, which is very catastrophic problem for autonomous driving, right? In which your car should stop when it sees this sign, but it rather sees it as a speed limit sign and then goes on. So there could be very catastrophic problems when we consider this adversarial attacks. So in the future of the object detection, we have to consider uncertainty. We have to come up with different evaluation metrics rather than average precision, and we should be able to have a continual learning in object detection algorithms, and we have to address these adversarial attack problems. Yeah, thank you for listening. It was all about my tutorial session. And if you have questions, I would love to have a discussion with this topic.
Hi, thank you, Alisher. We do have about 15 minutes remaining for questions. So if anybody would like to post questions in the chat or the Slack Q&A, I can read them out, and the presenter will receive them as well.
Yeah.
And we'll keep this room open for about 15 minutes as questions may come in.
Feel free to ask any technical questions, or we can just discuss about general topics about object detection.
I actually do have a question.
Let's go ahead.
On it looked like the latest method from 2018 was called RetinaNet. Is that the latest, or is there something newer
There is. For example, efficient that is proposed later than the RetinaNet.
Okay.
And I believe that there are lots of different object detectors as well. But I feel like these 5 are the biggest milestones in object detection. Yeah.
Okay, thank you.
Yeah, welcome.
Yeah, we'll keep this room open for about 5 more minutes for more questions, if you don't mind. Okay, thank you.
Thank you.
Looks like we have about 7 attendees still on. Before the time ends, I just wanted to say thank you to Alisher and thank you to all the attendees for this session. We're grateful to everyone. And at the conclusion of this GoToWebinar, I'll end in just about 2 minutes now. There will be a short survey, so please complete that. This survey helps us shape future conferences. We love data too here at ODSC. If any questions come up after the ending of this webinar, the Slack channel, which is the link for which is posted in the chat, is going to be active after this session. So you can always follow up with questions there. Thanks to everyone. I'll close this call in about 1 minute.
Thank you very much. Thank you for listening. And thank you for organizing.
Sure, you're welcome.